Okay, so let's start out this video by talking about F5 DNS performance. So as we continue along in the 302 exam blueprint, we're now looking at Objective 104. Okay, so Objective 104 explains or illustrates determining the performance requirements for a big IP DNS solution. So we're going to relate the performance characteristics of a virtual edition and physical hardware to a specific use case. We'll employ topology load balancing to optimize user experience based on the geographical location. And we'll predict the performance implications pertaining to key DNS features like DNSSEC and topology load balancing. Okay, so now let's take a look at Big IP DNS Virtual Edition versus hardware. So Virtual Edition, you're able to get virtual editions that increment in 250K response per second, which is about 1 gigabit per second of throughput. Now you can get a 10 gigabit per second VE, but it requires NICs that support the SRIOV function. So the SRIOV function is a single root IO virtualization which allows different virtual machines in a virtual environment to share a single PCI Express hardware interface. And the F5 can also support a 40 gigabit throughput option using an approved NIC adapter. So currently there is one approved, and it's the Intel NIC adapter XL710, and that requires you to be on F5 version 13, HFA2, and later, and also use the SRIOV function in your hypervisor. Okay, so you can see down on our list the most supported, or the highly used platforms, I guess you could say, support some of the high-end throughput options. So like AWS is supported on 10 gigabit per second VEs. The VMware vSphere, if you're doing on-prem or off-prem vSphere deployments. KVM and community Zen servers can use the 10 gigabit VE and also the Zen server. Okay, and things start to get interesting when we talk about hardware options. So the F5 obviously has hardware options that support a 40 gig throughput. If you wanted some additional capabilities, when you start getting to the 5050S platform, you can turn on the rapid response mode, which uses DNS Express to deliver a 200% increase on your max query response per second when it's turned on. You can use DNS Rapid Response to protect your network from DNS flood attacks on those specific domains. Okay, and obviously the higher you go in the platform scale for the F5 hardware, you can use more system resources. The Viprion B4550 blade currently supports over 10 million queries per second because it's able to take your max query response per second times 200 when using RRM, which basically gives you a 12 million response per second, which is over a 10 million response per second query able to handle per second. So very fast. Okay, and so when we're talking also about the SRIOV function, I wanted to talk a little bit how to deploy that. So when you create the F5VE to configure the SRIOV on the guest, you add 3 PCI device NICs and map those to your network. So normally when you deploy a VE, you'll get the management network and then external, internal, and HA. You would delete those networks in vSphere and leave the source network of management. Then you would edit the settings of that specific F5 virtual machine and add the PCI device. So if your hypervisor was set up correctly, you'd see 16 virtual functions on each port. You'd map those respective device to the respective VLAN for your internal subnet, and then you would repeat that process for your external VLAN and HA VLAN to use the SRIOV function. Okay, so let's take a look at a real world example when we're talking about virtual editions versus hardware. So you can see here we've got virtual editions used on the inside. Ideally, putting your DNS at the edge would be most effective, but here we're not handling a ton of DNS traffic, so we don't have to have a virtual server present, or if we don't have a virtual server present at the edge, say you don't have a vSphere environment that is connected to the edge of your network, I see it totally acceptable to place it inside the DMZ, especially if it's not handling a lot of queries. If you do have a physical model, I think your first thought should be placing it on the edge of your network in front of your firewall, because that allows the big IP DNS to do a better job of securing and handling DNS threats as the first line of defense. Okay, so this is an example or a recommended architecture for hybrid data centers that F5 provides. And in relation to what we're talking about with virtual editions versus hardware, you can think about maybe placing the virtual edition, so every diamond and blue represents the point of control that you are able to facilitate with the F5 DNS platform. You can basically use the VE option at each point or the hardware option. So depending on your environment, it may have different needs. So maybe a smaller VE in a certain tier would work better for your needs, and then hardware at the edge. So we could think about the tier 1 network providing network security and DNS, and then for the physical data center, we're able to provide the app delivery and acceleration to our database servers. And then over here is more of the GSLB functions, providing, again, network security and DNS to our corporate users, to go into a virtual data center, now supporting applications at that layer. And then we also have the third hosted provided model, which with cloud, using distributed GSLB functions to provide the same DNS and application availability for on-demand computing for your cloud hosts. Okay, so let's talk a little bit about big IP DNS topology, and we'll keep in mind comparing it to the performance benefits you get from topology. But since we're here, we'll also talk about how topology DNS works. Okay, so topology regions can improve the load balancing performance. You can basically take 10K topology records and turn them into one entry for all requests. So this obviously speeds up the process used for an internal lookup from a DNS server. Okay, the default topology priority uses longest match. So this is basically taking the closest, the LDNS server where that resides. It's going to look up all these characteristics from that LDNS source, and whatever it considers most specific, it's going to use that entry to point to the destination that we want to go to. And the more specific we match on the LDNS, the order it's going to take in the order of rules. All right, so the first thing it looks at is the CIDR format. So if we have a /32, it's going to take that over, over any other IP address in that list. The next is region, ISP, state, country, continent, and the LDNS request source negation record, which that excludes an LDNS. The wildcard records are also the last option used. And you should note that when you're planning the topology for F5 DNS, you should consider placing the topology records in the order they appear in the configuration utility. So you should place the more specific topology records towards the top of the topology statement, and the less specific records towards the end of the topology statement. And you can use this change order button to change the order of the topology records. Okay, and the topology configuration methods for F5 really have three configuration options, or methods I like to call them. The topology for a wide IP is matching a specific pool, and I would use this if you have specific pools per data center. The topology at the pool level, I think of it as more of a global pool used in multiple DCs. So if the LDNS comes in from Peru, the data center is going to go to a single pool in South America. So it's more of a global process. And then there's also the ability to combine the wide IP and pool level options. Okay, so let's dive in a little deeper at the DNS topology for wide IP specifically. So we've got three flavors: wide IP, pool, and then wide IP and pool. Okay, so let's take this example. We have this basically maps a LDNS source 11.1.0.0.16 to a pool 1. So a New York client comes into an LDNS server. Second request goes to the GTM. Then the GTM will respond with a pool 1 that's currently in the North America DC. Okay. The next example, we'll jump to 5. Got a client in Peru, goes to the LDNS. If it matches that LDNS in Peru, that request will, according to the topology records, will be sent to pool 2, which is located in the South America DC. Okay, the third request, a tablet in Chicago, goes to its LDNS, which the LDNS IP address is 12.1.0.1, and that's going to match. That's not going to match any of our first and second order topology records. So it's going to go to pool 3, which resides in the North America DC. And notice how for the wide IP, it's more of a local setting. So when you have a pool that resides in the same DC, like pool 3 does not expand into both DCs. It's not like you could say globally connected. It's separate content that you wish to send to a client, right? Less for availability, more for specific. Maybe there's language change for a DNS site that you wanted to update the content for. Okay, so here's an example of big IP DNS topology, a pool method. And notice in this case, we are able to use the pool across multiple DCs. In this case, the US is a failover for Bolivia, and Bolivia is a failover for US. So US clients will still go to the North America DC based on their source, but if those pool members fail, then requests will start going to the South America DC. The same thing happens the other way, where the South America DC requests from the LDNS, and it goes to the South America DC. But if those pool members fail, then it'll start routing requests to the North America DC. So the difference here is that the pool is a more global pool used across multiple DCs, where the wide IP is data center specific. Okay, so now let's talk about big IP DNS topology, the geolocation. The geolocation basically is the topology that determines the origin of the DNS request and applies the traffic management. It's the database that the F5 uses to determine where it needs to send the traffic to. The geolocation database is updated once a month, and you can retrieve that from F5's website. For IPv6 addresses, it's at the information stored is at the continent and country level. For IPv4 addresses, it's at the continent, country, state, ISP, and organization levels. Okay, what's really quite fascinating is you can actually purchase an additional license for geolocation at the city level. So if you have a really dense population area that you're trying to really get specific and serve clients that are close together, you can use that additional license to provide that geolocation data. Okay, so you won't see the ISP or organization details in the GUI, but you can use the whereis irule command to access this data and manipulate the traffic management. So like when we're creating the topology DNS records, you won't be able to select, hey, if the client's coming from this ISP or this org, determine where to send it, but you can use that where is I rule, if that makes sense. The default IP geolocation that F5 stores this information is in the user share GeoIP version 2 directory, and the updates go in the shared GeoIP version 2, which is probably a little more space to store those files. Okay, the GeoIP underscore lookup can be used to, it's just a tool that you can use to identify what the F5 would respond back with. So we can, in this case, look up and point to the GeoIP org specifically .dat for the 65 address. In this case, in bold, we see the f5networks.com or F5 Networks organization for that GeoIP record IP. So if you wanted to verify a specific IP address on what you think should happen, this is a good way to do it, and then you can create the topology records around that specific data you just looked up. Okay, so let's talk now about Big IP DNS, eDNS. It's a similar method used for topology load balancing. And what this does is it corrects an issue when clients use a centralized DNS resolver like Google DNS and OpenDNS. And there's some reports that basically say that Google DNS and OpenDNS comprise of 20% of worldwide DNS traffic, according to some reports. So what eDNS does is it injects information about the original client IP subnet in the DNS request. Because if clients are going to a resolver that is in another geographical location, we might get back a geographical location for that Florida server or a host that's close to the Florida location. In reality, we wanted to go to somewhere that is close to Brazil. Okay, so to test this, we can use a dig with in bind. There's in bind 9.10 to simulate the LDNS. We can use a dig with the plus subnet equals feature that sends our original client IP subnet in the request, and the LDNS will have to support this. Okay, so the OpenDNS currently you have to whitelist your host name and or zone to get that to work, and Google DNS auto detects the ECS support for your authoritative name server. Okay, so there was a draft eDNS iRule that was used when eDNS was still in draft format, not yet to be finalized, and F5 was working on just a basic iRule to set and identify where, based off the eDNS subnet that it gets, then it will set the location for the LDNS server properly, and pass that traffic to the appropriate actual local DNS server. So again, let's look at our problem case. So if a client in Brazil was using the OpenDNS, OpenDNS doesn't have any DNS servers in South America currently. So someone in Brazil using OpenDNS will likely hit an OpenDNS resolver in Florida. And the F5 will then think that the user in Florida, the user is in Florida, and as a result it will serve the content to the user in Florida, which is not close to Brazil. So that results in a slow, high latency experience for that user. So wouldn't it be nice if there was just a easier way than developing this iRule? Well, there actually is. There in version 14, there is a simple method to prefer the client subnet. So in the DNS features section for the profile, we disable bind. We insert the source address into the client subnet option, and because we're able to insert that source address, then we can prefer the client subnet for our topology records. Really nice feature that came out in version 14. Okay, so let's take a holistic look at the Big IP DNS performance benefits from various options. Okay, the F5 GTMD can work now across multiple cores, and that was back in version 11. So instead of a single core, it's used to distribute that load across, its 8-core system or more. Okay, it does not suffer from firewall bottlenecks because the Big IP DNS is a ISA lab certified firewall. And you're able to scale up to 200% of your RPS with rapid response mode enabled, and that's with the 5500 platform S and up. And then it provides 500 times the performance of a traditional bind server. Okay, utilizing DNS Express allows you to deliver a high-speed response and DDoS protection with in-memory DNS, and the configuration size, for tens of millions of records, able to store a ton, especially more with the updates in version 14. Your authoritative DNS is served out of RAM, and you can then scale and consolidate your DNS servers because you're able to handle all those zone transfer requests and not take the load off all these requests for your DNS servers and put them on the F5. You can bring DNSSEC to a non-DNSSEC environment. So say you have a cloud DNS environment that is set up to sign zones via DNSSEC. Well, you can replicate those zones to a traditional environment, and that now brings DNSSEC to non-DNSSEC environments. With DNSSEC validation, administrators easily offload and validate DNSSEC on the client side using Big IP DNS for resolving. This results in superior DNS performance and dramatically increases in the site response to subscribers. Also have high-speed logging, which essentially another method for Big IP DNS to use memory to serve out the logging it has based off TMM, like the actual CPU in TMM for logging. So it provides a much faster recognition of DNS functions and logs for our DNS queries and responses. And DNS caching is another method we can use for performance. Answering from cache is much faster and allows caches and also caches DNS responses for multiple clients. Okay, so here we have an F5 DNS acting as an LDNS for different clients using different features. So the first flow for the blue is used as a caching resolver for a reputable company with no DNSSEC. So we're using the caching resolver function. And then for let's say DNSSEC, a reputable company with DNSSEC, we're able to provide validation for DNSSEC to our clients. Okay, let's talk about our last Big IP DNS performance feature called Big IP DNS IP Anycast. Okay, there are 3 benefits for IP Anycast as it relates to Big IP. And this is basically allowing you to take multiple Big IP DNS boxes and answer on the same IP address. So you're spreading the load across multiple devices. So let's say we have the same listener address used across multiple locations. We're able to share that load, and this basically does 3 things. It improves the reliability because DNS queries are sent to one IP that's supported by multiple systems. And using BGP, the Border Gateway Protocol, we're able to dynamically remove that route if it becomes unavailable for our use based off the BGP Open Standard Protocol. Okay, the additional benefit, the second benefit, is the performance, because it's improved by routing queries to the nearest data center based off BGP. And the third is distributing the load across multiple systems, which helps mitigate distributed denial of service attacks. This distributed means they're coming from multiple sources. Okay, so let's walk through the implementation of this on the F5 DNS. So first we'll need the ZebOS routing license or the advanced routing module license. After we apply that license, we can do a ZebOS enable protocol. In this case, it would be for BGP, and establish a BGP peer with the upstream router. There's configuration guides available online for F5. Then we would create a DNS profile and apply or modify that profile to use bind server on the big IP. And this is the profile that's assigned to our unique listener. Okay, so we create a DNS listener and we enable under the listener a route advertisement setting that allows you to basically just take that IP address and advertise it in BGP. And we'll use the floating self IP if the big IP DNS systems are set up in HA. And it's recommended not to use the address, not to use an address that matches the self IP address on the system. So once that's complete, pairing BGP and with advertising the listener address, then we can use the show IP route and the grep for the listener address to make sure it is being advertised out to the upstream router. Okay, so in summary, we talked about the performance benefits we have for the VE and the hardware options. We employed a topology load balancing method to optimize the user experience, and we predicted the performance implications pertaining to key DNS features such as DNSSEC and topology load balancing. We also looked additionally at eDNS and IP Anycast. I had a lot of fun in this one. We'll jump up next is section 2. We'll discuss the implementation side of F5 DNS. I'll see you in the next one.